So the first is programmed I/O. What programmed I/O is? So programmed I/O, I'll be trying to explain with these two figures. So what programmed I/O is? A programmed I/O is an approach where a program, it goes to the busy waiting state. Busy waiting state, the name itself says, it is not a waiting state. So what happens in a busy waiting state is, in our previous discussion we already had a discussion that uh, there are a set of registers which are called status registers, which are associated with the I/O device, and these registers, they actually tell the status of the device, whether the device it is ready or not. So the program, it goes to the busy waiting state where the processor, it is repetitively checking the status of the I/O device, whether the I/O device it is ready or not, and also it is checking the status of the buffer for the availability of the data. So meantime the processor, it is not doing any work. So in programmed I/O, the program, it goes, the processor, it becomes idle for the amount of time the availability of the data it is there. So I/O device, it will be asked to complete an operation. So until and unless the operation it is completed, the processor, it goes to the busy waiting state. So let me try to explain the phenomena by means of these two diagrams. So program is there. Program is there in step number 1. So we are thinking of a phenomena where the program, it made a call for an I/O device. So what it will do next is, it is going to read the status bit and test whether the device is ready with the data or not. So if this, while performing this operation, the program or the processor, on behalf of the program, it is able to find out that the status bit it is set, then what is going to be done? If the value, the status is ready, then in that case, reading of the byte is going to take place. And then what will happen in step number 3? In step number 3, you will be testing whether more read is to be performed. So if more read is to be performed, again you will be checking the status of the device, and then you will be checking for the availability of the data. If again yes, then again you will be reading the byte. Again you will be testing the byte to be read, and this is something which is repetitively done. And meantime the processor, it sits idle. It is checking the status of the bit, and then so this is something which is called busy waiting. And when if in case the input is not ready, then it will be waiting for a period. So there will be a period when it will be waiting for, and if the waiting period is it is completed, and the device it is ready, again the reading of the byte it takes place. So again and again and again, repetitively, the bits, the status bits, they are checked. If the device it is not ready, then it will be waiting, and this is something which will be repetitively done. And when the operation it gets completed, you will be moving to the next step of the program. Now this is something which will happen when reading of bytes it is supposed to take place. Now when writing is something which is supposed to take place, then in that case the framework is almost the same. The difference is, so there is an input register or input buffer is there in the I/O device, and there is an output buffer or output register. So these two registers, they will be utilized while performing the task. So again, while writing, the program is going to be there. In first step, read status bit and test whether the device is ready. If it is ready, write bytes, and then test more bytes to be written. If the condition it is yes, then again read status and test whether the device it is ready. Again, if the device is ready, writing of bytes it will take place, and this is something which will take place until all the bytes they are written. When all the bytes they are written, you will be moving to the next step. Meantime, if a status it is acknowledged where the read status when you are checking and the device is not ready, then you will be waiting for a period, and this is something which will take place. So programmed IO is a case where the program is there, it issues an IO operation and it busy waits until the things, whether reading operation is there or writing operation is there, it is completed. For that period, waiting is something which is done. Now I already told you about the example. The second example will be coming on next is interrupt driven IO approach. So before speaking on that, we have to make a consideration of the example which I gave you. So the example, it was speaking of a phenomena that there is a program and a set of characters are there, and these set of characters they are supposed to get printed onto the printer. So when you make a consideration of the speed of the processor and the speed at which the printer it performs its operation, there is a big difference. So when a printer it is performing the printing of one character, the time that which it takes, the time in that time period, the processor it may actually perform a context switch and it can perform operations on another process. So despite of doing things in the way that which we had a discussion, that is programmed IO, where the processor it goes to the waiting state, it goes to the busy waiting state, which is not a waiting state. So until and unless the operation it is accomplished, it is not moving anywhere further, it is not giving consideration to any other process. Rather than that, it is waiting for the operation to get accomplished. Another approach it could be interrupt driven IO approach. So to have an understanding of this, first of all see this figure. Now this figure it speaks of four IO devices. There is disk, there is a keyboard, there is a clock, there is a printer. Now with these devices there are different associations. When you are thinking of a disk, the time that it will take to perform a disk operation, it will be doing things in terms of blocks and it takes some amount of time. When you are thinking of larger things, then disk operations, it takes some time. We'll be having a discussion on this in a short while. So keyboard is something where the responses they are asynchronous in nature. So what you are going to have out of the keyboard, you cannot make a prediction. So processor it cannot make a prediction at what time a person he is going to press the key. So the event is asynchronous in nature, but for this asynchronous event also, the processor it is supposed to respond in a positive way. So there has to be some framework. So interrupt driven approach is the framework, and also you can think of, now I gave you example of printer. So a printer it takes for printing one character it takes 10 some milliseconds of time. So when you are thinking of a disk operation of like kilobyte transfer of data is supposed to take place, then in that case more amount of time will be required. So if the processor it sits idle for that much amount of time, then in that case we are basically missing out many CPU cycles, and that which must not happen. So this approach it is a solution to the problem which I just specified. So here in this case the CPU is something uh, which is going to speak of the device. If a read operation is supposed to be performed or a write operation it is supposed to be performed, then in that case it will issue the command, and then it will continue with its work rather than going to the busy waiting state, and then it waits for an interrupt to come out of the IO device. So when the IO device, like here in this case disk is there, so when disk it is able to complete the operation, it will signal it via an interrupt. Or if a keyboard is there and it want to have the response of the processor, it is going to signal it via an interrupt. If a clock is there, it is going to signal it via an interrupt. If a printer is there and the operation it is accomplished, it is going to signal it via an interrupt. And then there is an interrupt controller which is supposed to take on all these interrupts. So interrupt request is there, and for acknowledgement you are having the interrupt controller. Now this interrupt controller, it could be a part of the processor or it could be an external unit also. So this interrupt controller, it takes on the signal and then it passes the signal to the CPU, and then after CPU it makes an acknowledgement, it reverts back to the interrupt controller, and the things they are passed to the various devices. So we'll be seeing this in a more explanatory way. We'll be seeing this in a more we'll be exploring this in a more emphasized way. So now this is the structure. These two structures are there. So before we try to have an understanding of interrupt driven IO, there are again it require a support. So whenever a policy is there that is supposed to have an implementation, then it require a mechanism, it require a support, so that things they are going to get accomplished. So interrupt driven IO, there are two lines. So there is one line that is called INTR line, and there is another line that is INTA line, and there is a flip-flop that which the processor it is associating with. So INTR line, it is basically meant for accepting the interrupt coming out of a device. So INTR line is for that purpose, and INTA line is for the acknowledgement purpose. So in INTR line, the interrupt request will come, and this flip-flop it will detect that, and then after making a detection it will pass on the acknowledgement. So beside that there is a concept of interrupt vector table, and interrupt vector table is something that which you can think of vectors, and these vectors they are associated with addresses, and these addresses are basically the addresses of interrupt service routines or interrupt handlers which are going to get invoked. So when an interrupt it happens, then the interrupt service routine invocation it takes place. interrupt service routine invocation is almost similar to what happens when a program is there. It makes a call to a procedure. So what happens over there, uh, uh, this is something which is same as that. So here what happens when an interrupt it is acknowledged, the invocation of the interrupt service procedure, interrupt handler is going to take place. In interrupt service routine invocation is going to take place, the execution it is going to happen, and the resolution of the interrupt it is going to come. So this figure it speaks of that. I already told you that we'll be having an interrupt handler logic. So like here interrupt controller was there. This is something which could be a part of the processor architecture, or it could be a separate construct. So and then there is now this figure, it speaks of masking. So there are various interrupts. Now think of a program which is doing operation on a critical section. So critical section is an area which is being shared by a number of processes. So when you are in the middle of doing some modification in the critical section, then at that time if interrupt invocation it happens and you are not able to do the things in a consistent way, then in that case the shared region it is going to become inconsistent, and you don't want that to happen. So what actually happens is some user programs, there will be a set of instructions by means of which you can actually disable an interrupt. So this is what is called the masking. So if a user program is there and it is able to mask or disable an interrupt, then uh, those interrupts they are called the maskable interrupts. But there will be the user program, there will be through instructions the user program may not be able to disable certain set of interrupts. So those interrupts they are called non-maskable interrupts. Non-maskable interrupts are interrupts the user program they cannot make a masking of, and maskable interrupts are something where masking it is something that which is possible. So there is a provision of interrupt request mask register, and this register it comprises of a set of bits, and there is a bit that is called EA bit. And there will be another set of bits from E0 to En. We can have a number of bits. Now these E0 to En bits they are actually specifying that now there could be a number of interrupts which you want to mask, all the interrupts you want to mask at the same time. So what you will be doing is you will be the EA value will be set to 0. So if EA value it is equal to 0, then it means that all the interrupts they are masked. Whereas if EA value equal to 1, then in that case you can think of a selection that out of the various interrupts, like E0 is there, E1 is there, E2 is there, and up to En, so many values are there. So if you are interested in masking only interrupt E1 and E2, so you will be setting the values of E1 and E2 to 1 1 each, and then you will be able to mask those interrupts. So this is this diagram is actually specifying of that phenomena. I already told you that INTR is the line. Interrupt INTR line is there, and through this the interrupt request it is going to go to the processor. and interrupt handler logic is something which could be a part of the processor, or it could be an external component also. So the request, so interrupt, it could be from device 0, interrupt it could be from device 1, interrupt it could be from device n minus 1, and this interrupt request, it will go to the interrupt handler logic, like here also. So it goes to the interrupt handler logic, and then in the INTR line, the interrupt handler it forwards it to the processor, and then the processor acknowledges it via the INTA line. Then after the acknowledgement it is made by the processor, then context switching is what is going to be done. So if interrupt it is enabled, then in that case you will be, we'll be checking with this interrupt request masking register whether the interrupt it is enabled or not, or it is disabled. If it is disabled, then in that case you cannot go further. So if it is enabled, then in that case context switching is something which is going to take place of the current program. You will be saving the state, and then you will be going to the processor, and then from the processor you will be moving to the interrupt vector table. So a number of interrupt vectors will be there, and these vectors, they will be storing the address of the interrupt service routine, which is basically a procedure that is supposed to get invoked when a particular type of interrupt it happens. So we are getting in a step number 5, we are getting to interrupt vector table, and the address of the ISR is something which is going, which we will be having, and the processor is informed of that. And then what the processor it does is, it is going to make an invocation, it is going to make a call to the interrupt service routine. So interrupt service routine is going to get called, it is going to make an execution, and then the return from interrupt service routine it is going to take place, and then next steps of the program they are going to have an execution of. So this framework, it speaks of the second strategy, that is interruption strategy. So in this strategy, still some amount of time, some CPU cycles will be making a utilization of, like as I told you, if you are thinking of a printer, then in that case the printer, the speed of printer, it is far the speed of processor, it is far superior than the speed of the printer. So we will be making a lot of loss of CPU cycles if you are going to the busy waiting state. So rather than doing things in that way, that is in programmed IO way, we are doing by interrupt, by making an invocation of the interrupt and doing things. But still, if you are going by this way also, there are certain problems. So what the basic problems are? So think of now in the same case, if a set of bits, if a set of characters are there, and those characters, they are supposed to get printed via the printer. So after every character it gets printed, the processor it is getting interrupted. So if 5 characters are there, 5 interruption will be there, and for 5 times there will be invocation of interrupt service routine. So interrupt service routine sometime will go away. So again you are losing some CPU cycles. So another approach it is specified, and that approach it is called direct memory access, where what happens is the IO device, so in the previous approach CPU was something that was involved in performing the data transfer activity, So in direct memory access, the IO modules, the IO devices, they are given the authority to deal directly with the memory. So via the DMA controller is going to be there. Now DMA controller concept is, you can think of DMA controller is something which is appearing even in the devices. The devices, they are having the DMA controllers. But if you are having the various devices, they are having different DMA controller, the approach is not going to be very efficient. Rather than that, you can have a DMA controller in the board, and that DMA controller, it could be making a control of the various IO devices. Although different configurations are there, you may be seeing a configuration where a separate DMA controller, it is associated with an IO device. So DMA controller is something which is going to provide something to the IO device. The something that which is provided to the IO devices, it is given the privilege, the IO device is given the privilege to make a direct interaction with the memory modules. The memory direct interaction, it could be there. So how DMA it basically operates, let us have a look on that. So DMA controller is something that which is required for this purpose. And memory bus is something that which is utilized. So before moving to DMA controller, there is one more thing that was missing out, and that is bus arbitration process. So what bus arbitration process is? Bus arbitration process, it refers to a process by which the current bus master accesses and then leaves the control of the bus and passes it to another bus requesting process unit. Requesting the processor unit. So there are three bus arbitration methods. There is a method that is called daisy chain method. There is a method that is called independent bus request and grant method. There is another method that is called polling method. So all these methods are there for bus arbitration. So the thing is, there is a bus. This bus is there, which is supposed to be shared between all these units. A processor is there, controller is there, DMA controller is there, IO processor is there. So what IO processor is, you can think of IO processor which is also having same sort of thing what DMA controller is having. DMA controller is something which is used for interfacing of the various IO devices. So IO processor is something which is also having a similar sort of thing. There will be IO devices, and these IO devices, they are given direct privilege to have an access to the memory. But IO processor, they are having one more thing which DMA controller they are not having. So processor, they are having a set of instruction set on which these processors they actually operate on. So likewise, IO processor, what extra thing they are having, if you are making a difference between a DMA controller and IO processor, the extra thing that you will observe in IO processor is, IO processor, they are having an instruction set. Like the processor, they are having instruction set. Although the instruction set that which is allowed